Hello, this is Sebastian Lerich from the CloudScale project. In this screencast, I'm showing you how to conduct analyses using the CloudScale analyzer. And as an input, we use the previously specified ScaleDL model instances we created. So for a guide how to create such models, please see the previous screencast series. Now we focus on this part, the analyzer, where we use that as an input. We also configure the analyzer for an analyzer run. And at the end of the series, we will in particular have a look at the output of the analyzer, which states how the system behaved for our ScaleDL model instance. So we can investigate properties such as elasticity, efficiency, scalability, and we have also some capacity metrics at hand. So let's dive into the analyzer. First, I'm going to show you now how to configure the analyzer. And we do that with an additional configuration model for the analyzer, which is called experiment automation. So we switch to our CloudScale environment, and I again have opened the Cloud Store example as available in our Git repository. So there you find a folder called experiments, and if you open that, you see that there are some models that end with experiments. There are launch configurations that then start such experiments. And there is a variation file which is always the same for each experiment. So this is generic and can just be copied. So the purpose of such an experiment is to configure what the analyzer should do in one analysis run. And to conduct such or to specify such an experiment model, the easiest way is most probably to copy an already existing experiments file, depending on the kind of analysis you want to conduct. So in this example, I pre-specified two different experiments, one for capacity analysis and one for an elasticity analysis. The capacity analysis can also easily be turned into a scalability analysis. So that's the first thing you have to think about, what kind of analysis you want to run. We start maybe with a capacity analysis. So as I said, the easiest way is most probably to copy an existing model file. So we can right click here, say copy, right click on the folder, say paste, and we may just create such a copy here. Okay, so now we can open this file. Okay, I opened it now in the text representation view. The good thing about this, we have to change something here for your purpose. Currently our UI is a bit limited at this point because we have to manually adapt the location where to store measurements here. So have a look for this location attribute of the data source tag and adapt it to your needs. So on Unix-based systems, it would look like something like this. So users, your username, and some directory where to put data in. On Windows, you should try it with something like this user data, username, something like this. Okay, so that's the first thing you should always do, adapt that location attribute to your needs. So I will of course go with the configuration I already used before. On my hard disk you will also find a set of pre-existing experiments here, or experiment runs here. I can also delete them, so we can have a really new run for this screencast. But that's all you have to configure here in the experiments text file. For the other things, you can actually use the tree editor. So right click on the experiments file, open with experiments model editor, and here you get to see the normal tree editor for EMF models. So open the properties view and investigate what I configured for this experiment. So experiments are organized in repositories. Here is only one experiment included in this repository. This experiment is named one cloud store browsing capacity analysis. So that's the name attribute here, because that's an experiment that actually uses the browsing mix usage scenario from the usage scenario folder, and it conducts an analysis for capacity, answering the question with how many users my system can cope with. So the output should be a number, the total number of users, what is the maximum number of users, okay? So, so that's where the name comes from. There can also be a description. There can be an ID of this example. So that's the experiment automation example, maybe. There can be a number of repetitions of this experiment. That's especially useful if you question the statistical significance of your experiment. So instead of just conducting it once, you may conduct it 10 times, and then you can compare the different runs, maybe build up distributions, whether the outputs change, how stable your output is, etc. But I will go with one run for the time being here. So for the tool configuration, you should always use this pre-configured tool configuration for Simulizer, because Simulizer is a tool that comes with support for self-adaptations, and we need that for several analyses for our purpose. So that should be correct. So we can move on to the next property here. So an experiment can have a set of child elements. As you see here, when you right click and choose new child, there are a set of possibilities you have to, or you can choose from. We have a look now at the concrete childs I entered here. So let me start from bottom to top, maybe. So that's one of the most important child elements. It's called the initial model, and it essentially links all the model files that should be considered in this analysis run. So in our case, I specified two repositories here for event middleware and for the middleware. They are generic and they can always stay like they are, as long as you stick to our default event middleware and middleware implementation we measured for Palladium. Of course, you also have to specify the usage model and the allocation, which come as part of the extended PCM. So the usage model in particularly links also the system model. The system model also links the repository model. The allocation also links the system model as well as the resource environment. So it's enough actually to just enter the allocation and the usage model. The remaining models can simply be found based on traversing these models and following up their links. What is still missing for a capacity run is you have to specify service level objectives. So We previously have seen how to do that. We may have a 3 seconds SLO. We can also investigate which SLO I linked here, so you will find it in the tree editor here. So there is an SLO, 3 seconds actually, and okay, here I reconfigured it to have a threshold limit of 1.5 seconds. You will just see how that affects the analysis. So we have an SLO of 1.5 seconds, and we have that at which usage scenario? We can investigate the measuring point. It's the usage scenario measuring point of the browsing mix. Okay, so back to the initial model. So we have to specify the service level objectives. We should also specify a PMS model, a platform monitoring specification model, which allows you to state which metrics are of interest for you. So, for instance, you may be interested in the response time usage scenario. You would put that into a PMS model, or you may be interested in server utilization, etc., etc. I pre-configured such a PMS model and attached that here. The PMS simply comes with the Simulizer tooling, so the extended PCM, which was already existing before this project started, this kind of model. So you just have to specify these inputs for such an experiment, and then the analyzer can understand what are the inputs, and it takes the inputs simply. So let's investigate the other properties. So there is this is a simulation duration measurement, which means we measure the starting point of a simulation run or an analyzer run and the endpoint, and then we can calculate the total duration of the simulation. That's a nice default property because it's some kind of useful information to know how long your simulation took. We have a full factorial design, so experiment automation allows to vary parameters in an experiment, and then run experiments with varying parameters. The full factorial design tries out every possible combination of such parameters and runs for each possible combination a single experiment. We have a stop condition here, so I took a simulation time stop condition for this variant. I want to stop after 30 time units, which relates to each single experiment run. So one experiment run for one variation according to the full factorial design took a maximum of 30 seconds. I also added a measurement count stop condition, but I use the default value, which is -1, meaning that we ignore the measurement counts. We don't use that as a stop condition, essentially. Finally, you also see the variation of user capacity, which is probably most important characteristic. So that's the property that enables you to run a capacity analysis by varying a certain variable within the project. So what we vary is this ID specified here via the unique identifier of the object. That has to be always in the usage scenario. And if you open the usage scenario, so remember this ID here. If you open the usage scenario, you will also find the ID here. By just clicking on the usage scenario, you will see that this ID is the same as I have previously shown to you. So that's the usage scenario where we want to measure capacity for. And what this actually does is it varies the population number in this closed workload here and tries to determine what is the maximum number of users the system can cope with regarding the previously specified SLA as we entered in the initial model. So there are essence, we do some kind of binary search for determining this number. Therefore, we can specify a minimum value and a maximum value. You also see that in this nested intervals value provider here. That's a binary search between 1 and 100, trying to find the optimal number for the maximum number of users the system can cope with between an interval of 1 and 100. So if we find out the system cannot even cope with 1, then the system is in a non-usable state. If we find out the system can cope with 100 users, we can scale pretty good between 1 and 100. The capacity is most likely even above 100. So we could increase the investigation interval if you want to see whether there's a more upper limit. If that is enough according to our requirements, we are already quite happy with 100 users in our scenario. So having such a model at hand, we can create a run configuration for such a model, which is relatively straightforward. So I am going now just to use the existing run configuration I already have. So we may take the browsing mix capacity run configuration. The only real thing you have to do is you have to specify what is the experiments file you want to analyze. So you can just use the workspace button here and choose the experiment from this run configuration. So in our case, it would be in CloudScale store experiments, and then the copy of experiments, or I just leave it to the originals. So the original file, and I just say OK, so I did not change anything. I'm going just to run the capacity experiment for the browsing max usage scenario. So if I now say run, an actual analysis is started. So you see the workflow starting here, which may consume some time, especially for capacity experiments. Several sub-runs are executed. I forwarded an additional output of my experiment run to another Eclipse instance, you see here. And it gives you some detailed information about the concrete experiment that is now running. So in our case, we have the one CloudScale browsing mix capacity analysis experiment running. Since we have a capacity experiment, we vary different population sizes in a binary search style. So we started here now with a user capacity of 1, which is indicated by this 1 here. So that is the first test we run, and so we run this whole scenario now using this population size. So as soon as we are finished with the analysis of population size 1, we will see that another sub-experiment is started, which will test a population number of 100, which is the upper bound of our interval. So let's have a look at the simulation. It's still simulating. I still did not get any additional information here on the experiment. This usually consumes some minutes for capacity analysis, depending on the size of the model. Now we saw that one run went through. The next one is, as predicted, a run with 100. As I already know the model, I already can tell you the system cannot cope with a population size of 100. So the next value that experiment automation tests would be 50. And then it continues this binary search style until it found the real capacity of the system. So we will fast forward now to the end of the analysis.